All right, welcome to day 2 of our optimization lesson. So this is one where we're going to look at optimization problems that the candidates test isn't really a good option for. And we'll talk about why that is as we go through the problems. So we'll see our justification work a little differently on this. Okay, so we have a closed box with a square base that is to be built. So its volume is 72 centimeters cubed. Get my calculator working here. All right, so I'm going to draw a picture of a box. I'm not the best 3D drawer, but we will do our best here. Okay. Sorry about that. There we go. All right. So I'm going to say that this is my base right there. And so it has a square base. So I can label this side and this side both with X. And then our height will be a different value. So H. And then volume of this box would be X times H. So volume is equal to X squared H. And they tell me that the volume is 72 centimeters cubed. All right, so we have that equation. We'll keep that to the side for now, and then we'll come back to it later. All right, bottom of the box costs 60 cents. The sides cost 35 cents per square centimeter, and the top costs 30 cents. Find the dimensions and the cost of the least expensive box and justify your answer. Okay, so the function that we have to minimize because we're doing least expensive is a cost function. So I need to write out a function for cost. So I'm going to call it C. C is equal to, all right, 60 cents for the base. So base is X times X. So that's 0.6 X squared. Sides cost 35 cents. So 0.35 times, there are 1, 2, 3, 4 sides. So 4. And the sides are X times H, all 4 of them. So XH. Plus, in the top costs 30 cents, so 0.3, and the top has the same dimensions as the bottom, so X squared. All right, simplify, we can add our two X squared terms together, so 0.9 X squared, and then 0.35 times 4 is 120 plus 20, 1.4. All right, so the problem with this equation is it has 3 variables. We have C, we have X, we have H. So we want to only have 2 variables. That's what our volume equation over here is for. Okay, so I want to get either X by itself or H by itself. I want to avoid having square roots, so I'm going to get H by itself. So H is equal to 72 over X squared. All right, we're going to substitute that in over here in our cost equation, and this is going to make cost in terms of X only. So I'm going to call it C of X now. So I have 0.9 X squared plus 1.4 X times 72 over X squared. All right, let's simplify. C of X is equal to 0.9 X squared plus, all right, 1.4 times 72. I'm going to use my calculator for this one. 1.4 times 72. 100.8. And then X divided by X squared leaves me with an X on the bottom. Okay, so I now have a cost equation in terms of a single variable X. So we're ready to do the derivative and find our critical point. So C prime of X is equal to, multiply by 2, you get 1.8X to the first power, multiply by negative 1, so negative 100.8, X to the negative 2, so back down to the denominator we go. All right, to find our critical points, we set our derivative equal to 0. And solve. So I'm going to add this term over to the other side. I'm going to go this direction. 1.8x is equal to 100.8 over x squared. Then I can multiply by x squared on both sides. I can also divide by 1.8. So I get x cubed is equal to 100.8 divided by 1.8, right, which is equal to, let's go back to our calculator, divided by 1.8. 56. All right, and so that means x is equal to the cube root of 56, which is approximately equal to, all right, cube root of 56, 3.826. All right, so it's at this point where we would normally try to make a table and do the candidates test. Okay, but that's not a good option here. Remember, for the candidates test, you need well-defined endpoints. All right, so you want to think about, like, if we're making this box, what is the smallest number x could be? All right, you know that x can't be negative because it's a length. Okay, so you might be tempted to say 0. All right, and theoretically, that's the smallest number x could be, but you run into a problem because h is defined as this. H is equal to 72 over x squared. Well, if x is 0, then we have 72 over 0, which is not allowed. So what is the smallest number x could be, like 0.1 or 0.01 or 0.001? All right, you see where we kind of run into a problem here. It's not well defined. Okay, so we're going to use the fact that we only have a single critical point. So we're not going to do the candidates test. We're going to do this other method where, as long as the minimum, which is what we're trying to find, occurs at this critical point, then that has to be the absolute minimum because it is the only critical point that we have. Okay, so we're going to put this on a number line. All right, and our number line does have endpoints. They're just not well defined. So I'm just going to put endpoints instead of arrows there. And then we'll put our x value here, so 3.826. Okay, and we want to plug in a number on the left and the right, and we're going to plug this into the derivative, c prime of x. And we're looking for it to change from negative to positive, because that's going to tell me that this is a minimum. All right, so I'm going to choose x equals 1 over here. And I'm picking values specifically because they are going to let me evaluate this without a calculator. All right, I always want to try to evaluate without a calculator if I can. Okay, so if I plug in 1, then I just get 1.8 for that first one. If I plug in 1 here, 100.8 divided by 1 is 100. So it's 1.8 minus 100.8. Definitely a negative number. All right, and then I'm going to choose 10. Okay, and the reason I'm choosing 10 is because it's easy to manipulate with these two numbers. 1.8 times 10 is 18. So that's going to be 18. And then 10 squared is 100. So it's 100.8 divided by 100, which is a little bit bigger than 1. So I know it's 18 minus 1, basically, which is definitely a positive number. So I know my c prime changes from negative to positive at this point. And since it's the only critical point, that has to be our absolute minimum. Okay, so we have to write that out. All right, so we'll say x equals 3.826 is the only critical point. And c prime changes from negative to positive there. So it must be the location of the absolute min. Okay, so now we know our x value for the absolute minimum. Now we're ready to answer the question. Find the dimensions and the cost of the least expensive box. All right, so we know the x value. So the h value is the other dimension we need to find, is just this equation here. So h is equal to 72 over, I'm going to go cube root of 56, and then that's squared, because x squared. And again, we'll just use our calculator for this. 72 divided by cube root of 56, and that's being squared. 4.919. All right, and then the cost of the box is c of x, so c of the cube root of 56. All right, so c is going to be this one right here. Actually, this one right here. All right, so that is approximately equal to, I'm not going to write it out with the numbers plugged in because we're using our calculator anyway. So it's 0.9 times the cube root of 6 squared minus 100.8 divided by the cube root of 56. Verify I'm getting this right. Yes. So it was plus. So plus. All right, we get 39.52, and cost is in dollars, and dollars is always rounded to 2 decimal places instead of 3. So that's 39.52. All right, I'm going to write my answer out as a sentence over here, and then we are done. The cost of the least expensive box is $39.52 with dimensions of 3.826 centimeters by 3.826 centimeters by 4.919 centimeters. All right, let's try another one. Maybe give this one a try on your own if you're feeling comfortable enough with that. And then unpause the video and see how you did with it. Okay, so we have the dimensions of a 12-ounce can that can be constructed with the least amount of metal. Okay, they're telling us here a conversion. 12 ounces is the same thing as 355 milliliters, and milliliters is the same thing as centimeters cubed. Okay, so we are going to find the least amount of metal. So that's going to be the surface area of our cylinder. That's the surface area is the amount of metal that you would need to make a can. And then we're also going to need this volume equation as well. Okay, so they're telling me that the volume is equal to this. So that's 355 is equal to pi r squared h. Okay, again, like our volume equation from the last problem, we're going to use that to make a substitution later. Let's go over here. Okay, so we want to minimize the surface area. So I'm just going to label this as S. S equals 2 pi RH plus 2 pi r squared. Same issue that we had on the last problem. This has 3 different variables. We need it to only have 2 variables. So I need to get either r by itself or h by itself. Again, I do not want to use a square root with r, so I'm going to get h by itself. H is equal to 355 divided by pi r squared. All right, so I'm going to plug that in over here, and that's going to give me a function in terms of r. So 2 pi r times plug in 355 over pi r squared plus 2 pi r squared. All right, let's simplify. Let's see, the pi's will cancel, the r will cancel, so I'll end up with an r on the bottom, and then 2 times 355 is 710. All right, once you found your equation, take the derivative. S prime of r is equal to, multiply by -1, so negative 710, r to the -2, back down to the denominator. Derivative here, oops, not equals, plus 4 pi r. All right, so now we set our derivative equal to 0, and we solve for r. Okay, so we're going to get 4 pi r is equal to 710 over r squared. Going to multiply by r squared to get r cubed, divide by 4 pi, which is going to give me, I'm just going to leave it like that. We could simplify 710 divided by 2. You could go 355 over 2 pi if you prefer. All right, either one. So r is equal to the cube root of 355 over 2 pi, which is approximately equal to, use our handy dandy calculator again, 710 divided by 4 pi. Oops. 3.827. All right, just want to verify my simplified form is the same thing. There we go. All right, so 3.827. 837. 3.837. And we are in centimeters. All right, so same issue as last time. Like, what's the smallest value r could be? 0, but then that would give us 0 in the denominator. So not well defined. So let's try to do our number line method again for this. Okay, so I'll make my number line. I do have endpoints. I just can't define them very well. then I have my critical point, 3.827. Okay, and it's the fact that we only have a single critical point that makes this work. If we have multiple critical points, then you would have to do the candidates test. Okay, so just keep that in mind. Okay, so I'm going to try the same thing as last time. I'm going to try to pick some numbers that I know I can do without the calculator. So I'm going to go with 1. If I plug in 1 here, I get negative 710. All right, we're plugging this into S prime. And if I plug in 1 here, I get 4 pi. 4 pi is about 12. Okay, so negative 710 plus 12 is definitely a negative. All right, and then let's plug in like 10. All right, so if I plug in 10, I get 100. 710 divided by 100 is 7.1. All right, so that's negative 7.1. And then here I would get 40 pi. So 40 times pi, if pi was 3, that'd be 120. So it's like negative 7.1 plus 120, which is definitely a positive. All right, so it worked again. We have our minimum happening at this point, so we're going to write it out. Since x equals 3.827 is the only critical point, and S prime changes from negative to positive, there, then it is the location of the absolute minimum. All right, now let's answer the question. So find the dimensions of a 12-ounce can that we constructed with the least amount of metal. So all we have to do is find the dimensions, which means we're just left with h. H is equal to 355 divided by pi times the cube root of 355 over 2 pi squared. And this will be an approximation that we'll use with our calculator. All right, 355 divided by pi parentheses cube root 355 over 2 pi, and that whole thing is squared. 7.674. All right, let's write our answer out as a sentence, and then that will be it. All right, so the can that uses the least amount of metal has dimensions R equals 3.837 centimeters and H equals 7.674 centimeters. All right, hope that went well for you. I'll see you on the next video.